In example 15, we are told that two fair 10-pence coins are tossed, and the random variable x represent the total value of the coins that land heads up. Of course, the table is here. The total value of the coins that land heads up, when the hands up, there was nothing like hands up quarter, the probability was a quarter. When this one shows, when none of the coins shows heads up, the probability is a quarter. When only one of the coins shows heads up, the probability is a half. When both of the coins shows heads up, the probability is a quarter. And then we are expected to find EX and variance of X. Find EX. Let's first of all do this. EX, we know very well, it's the sigma of X times the probability of X. And one thing we must note is when X is 0, the probability is a quarter. So 0 times a quarter plus 10 times a half plus 20 times a quarter. Of course, this is 5 plus 5, which is 10. And that is our value of EX. What about the variance of X? The variance of X, as we know, is obviously given by the expected value of X squared minus the expected value of X, which is going to be squared. And the expected value of X squared, this part is sigma X squared, the probability of X, minus sigma X probability of X squared. Of course, we have this in part A, which is 10. So we just have to outline EX squared PX. We only have to square the value of X, then multiply by the probability. So 0 squared times a quarter is 0. 10 squared times a half, which is 100, which is 10 squared times a half, plus 20 squared times a quarter. And this one is 100 times a half, which is 50. And this one is 400 times a quarter, which is 100. Both of them put together will give you 150, of course, minus EX squared, which is 10 squared, giving us 100. And of course, the answer is 50. So yes, the variance of X, we have gone through all the steps and it's being realized to be 50. Well, part C, we have some more instructions. We are told that the random variable S and T are defined as follows. The random variables S and T are defined as follows. We can already see that our S is given by X minus 10, and our T is given by a half X subtract 5. Question: show that ES is equals to ET. Show that ES is equals to ET. Expected value of X is the same as expected value of T. We know very well from
sometimes back, especially in some two examples back, we know AS plus B is equal to AEX plus B. Now, ES, which is x minus 10, we are being told to show that it is a half x minus a 5. And this one is simply, when we substitute this one in this formula, the A is a 1, so 1 times EX, which is 10, 1 times 10, 1 times 10 minus 10, because eventually this one is going to be 1 EX minus 10, which is a half EX minus a 5. So 1 EX and EX, expected value of X is 10 times 1 is 10 minus 10. This one should be equal to a half times EX, which is 10 minus 5. Obviously 10 minus 10 is 0, and a half times 10 is 5 minus 5, which is equal to 0. So therefore ES is equal to ET, hence shown. And that is not the end of it. We should go ahead and calculate. We are told that to find the var of S, the variance of S, and the variance of T. Let's clear something here. The var of S, which should be the var of x minus 10. And if you look at this, the var of ax plus b, from the previous example, we have had that this is a squared variance of x. And this one, our a is 1. So the var of x minus 10, which is our x, is 1 squared multiplied by the variance of x, whereby we have found the variance of x in part A, which was just wrapped here, and it was supposed to be 50. The variance of x, the variance of x, as far as we are concerned in part A, is supposed to be 50, yes. And in this case, it's supposed to be var of x, which is 50. So 50 times 1, which is 50. But it is now the var of t, which we know is the variance of a half x minus 5. Please note that, as we have understood in the previous examples, the b does not affect the variance. The b does not affect the variance, and that is why we have ignored it in the last step of the var of s, which is now the a is a half. So a half squared times the var of x, which is a quarter, times the variance of x being 50 in the previous example, and this one is 50 divided by 4, which is 12.5. That is 12.5. So you can see that the var of s is not equals to the var of t. The variance of s is 50 and the variance of t is 12.5. Look at part D. We have some more instructions, and we are told that Susan and Thomas play a game using 2 10-pence coins. The coins are tossed, and Susan records her scores using the random variable S. and Thomas uses the random variable t. After a large number of tosses, they compare their scores. Part D. Comment on any likely differences or similarities. Comment on any likely differences or similarities. What we can say, even before we leave this part of the working, what we can say is that their total scores should both be approximately equals to 0. Because we can see the expected value of S, which is the expected value of X, which is 0, and the expected value of T, which is 0, we can say that both of their scores should be approximately 0. Both of their scores should be the approximately 0, or rather their total score should both be approximately 0. But having said that, we can also say the following, that Susan's scores should be more varied than Thomas' score. Susan's score, because Susan is using S, which is 10 x minus 10, and Thomas is using T, which is a half x minus 5. Susan's score should be more varied than the Thomas score. You can already see the variance of S is 50 and the variance of T is far less than 50, which is 12.5. Yes, as much as we are saying that their total score should be approximately 0, because the estimated value of S is equals to the estimated value of T, both of which are zeros, so their total score should approximately be equals to 0. But Susan's score is more varied than Thomas' score from the results that you can see out of the experiment and its calculations. All right?